Hello everyone, I am Jagdish Patel, Assistant Professor, Sandeep Foundation, Nasik. The name of subject is Digital Circuit, and this is Unit 1, Digital Logic Families. Today we are going to see in lecture number 2, Introduction to the Characteristics of Digital Logic Families. I am having 12 years of teaching experience, specialization in digital communication. The various characteristics of digital ICs used to compare their performances are listed below, such as first one is speed, second one is power dissipation, third one is figure of merits, fourth one is power out, power in, fifth one is voltage parameter, sixth is current parameter, seventh noise immunity, eight operating temperature, and nine power supply requirements. So these are the nine parameters, we can say characteristics on which the performance of any digital IC is best. So let's see one by one. Starting with the first one, that is speed of operation. The speed of a digital circuit is specified in terms of the propagation delay time. The delay times are measured between the 50% voltage level of input and output waveform. There are two delay times TPHL when the output goes from the high state to the low state, TPLH corresponding to the output making a transition from the low state to the high state. The propagation delay time of a logic gates is taken as the average of two delay times, that is TPD is equal to TPHL plus TPLH divided by 2. So this is the formula to calculate the time delay. Now in this diagram we can see the input and output section. Here this TPHL in the input section and TPHL in the output section, there is a time delay. Similarly, if you observe on the next hand side, TPLH for the input section and the output section, there is 50% of delay. So in this way, this is nothing but the diagram shows the propagation delay in terms of speed of operation. Next is power dissipation. This is the amount of power dissipated in an IC. It is determined by the current ICC, that is drawn from the VCC supply, and is given by PD is equal to VCC ICC. This is the equation to calculate the power dissipation, where VCC is nothing but it is equal to power supply voltage and ICC is equal to current used. ICC is the average value of ICC 0 and ICC 1. In general, ICC is equal to bracket ICCH plus ICCL bracket closed and divided by 2. So this is the equation which gives the value of ICC, and this power is specified in milliwatt. Digital IC terminologies for power requirement. Here, the amount of power an IC requires is determined by the current ICC, or it can be also written as IDD. It draws from the supply. Actual power is produced is product of ICC into VCC. In bracket we can also write, or it can also be written as IDD into VDD. In some logic circuits, average current is computed based on the assumption that the gate outputs are low half the time and high half the time. So it can be given as ICC average is equal to ICCH plus ICCL. divided by 2. In the diagram shown here, the plus VCC supply is given, which is shown on the top, and the same circuit is grounded below. Here it consists of NAND gate. So in each combination there are 3 NAND gates, and we are applying the inputs to the NAND gate and we are getting the outputs. The current ICCH is flowing from VCC inside the circuit. Similarly, on the next hand side you can see the same configuration is used, only the value of inputs are changed and the output values are getting different. But here the current which is entering in the circuit is ICCL, whereas in the first it was ICCH. So this is the difference between the two diagrams, comes under the power requirement. Now third one is figures of merits. The figure of merit of a digital IC is defined as the product of speed and power. The speed is specified in terms of propagation delay time expressed in nanosecond. Figures of merit is equal to propagation delay time nanosecond into power in milliwatt. This is the formula to calculate the figures of merit. It is specified in picojoules, PJ. A low value of speed power product is desirable. In a digital circuit, if it is derived, if it is desired to have a high speed, that is low power, low propagation delay, then there is a corresponding increase in the power dissipation and vice versa. Now fourth one is fan in. Fan in, input in bracket we have written input load factor, is the number of inputs signal that can be connected to a gate without causing it to operate outside its intended operating range. It is expressed in terms of standard inputs or unit load, ULS. Example, for standard TTL, one unit load is defined as 1 UL is equal to 40 microampere. In the high state, 1.6 milliampere in the low state to determine the fan in or fan out. For a gate, take the lower of a fan in of 8 means that 8 unit loads can be safely connected to the gate input. And in the figure, it has shown NAND gate with a fan in of 8, means having 8 inputs provided to NAND gate, and we are getting the output. Whereas the next one is fan out. Fan out is the output load factor, is the maximum number of inputs that can be derived by a logic gates. Example is a fan out of 10 means that 10 unit load can be derived by the gate while still maintaining the output voltage within a specifications for logic level 0 and 1. The maximum number of standard logic inputs that an output can driven reliably, also known as the loading factor, related to current parameters both in high and low states. This is the number of similar gates which can be driven by a gate. High fan out is advantageous because it reduces the need for additional drivers to derive more gates. So this is nothing but the connections for the different NAND gates which are connected in the configuration to obtain the high fan out. The fifth one is voltage parameters. So they are subdivided into number of types. The first one is high level input voltage, denoted by VIH. This is the minimum input voltage which is recognized by the gate as a logic 1. The next is low level input voltage, VIL. This is the maximum input voltage which is recognized by the gate as logic 0. Next is high level output voltage, VOH. This is the minimum voltage available at the output corresponding to the logic 1. And the last one is low level output voltage, VOL. This is the maximum voltage available at the output corresponding to logic 0. And in the diagram, the same has been reflected. If you observe here for logic 0 and this configuration is for logic 1, here this is VOH, that is high level output voltage. This is IOH flowing through it. This is IIL. This is VIL, that is low level input voltage. Now correspondingly same in the below. This is VOL, that is low level output voltage, and this is VIL, low level input voltage. And the current flowing through it is IOL and IIL. So this is the configuration for logic 0 and for logic 1 for the voltage parameters. The same has been reflected here also. Here VIH, that is minimum high level input voltage, the minimum voltage level required for logic 1 at the input. VIL max low level input voltage, VOH minimum high level output voltage, VOL maximum low level output voltage for TTL. For proper operation, the input voltage levels to the logic must be kept outside the indeterminate ranges. Lower than VIL max and higher than VIL min. If you observe in this diagram, this is for TTL. Here it is divided into three parts. The first is logic high. In between, by the pink color, it is unacceptable, and the last one is logic 0, that is low. So this means this is the voltage ranges which is given as the range between 0 volt to 0.8 volt is VIL range. The range between 2 volt to 5 volt is VIH range. This is VIL minimum and this is VIH minimum. So these are nothing but this diagram is nothing but for it is for input. Now similarly for output, here this is logic high section, this is unacceptable, and this is logic 0 section, that is high and low. Here the voltage ranges from 0 volt to 0.4 volt for VOL, and similarly 2.5 volt to 5 volt for VOH. Now next is sixth one, current parameters. In current parameters, the first one is IOH, that is current flowing into output in the logic 1 state under specified load conditions. Next is IOL, current flowing into an output in the logic 0 state under specified load condition. Next is IIH, current flowing into an input when a specified HI level is applied to that input. Next is IIL, current flowing into an input when a specified LO level is applied to that input. So here if you observe, these are the three gates. Here the current entering in the first one is IOH, in the second one is IIL, output of that one is IOL, and in third one there is IIL. So these are nothing but the parameters which are required for the current measurement of that particular IC under different conditions. Seventh is noise margin. The noise immunity refers to the circuit ability to tolerate noise without changes in output voltage. A quantitative measure is called noise margin. It is of two types, high state noise margin and low state noise margin. VNH is equal to VOH minimum minus VIH minimum, and the voltage ranges from 2.5 volt minus 2.0 volt is equal to 0.4 volt. This voltage is nothing but it is called as high noise margin voltage, which is 0.4 volt. Whereas for low state noise margin, it is VNL, that is no low state noise margin voltage, is equal to VIL max minus VOL max. This equation gives you the low state noise margin voltage. And the same has been reflected in the diagram below, which consists of the same logic 1, that is high section, between middle one is disallowed range, or we can say indeterminate range, and the last one is logic 0 section for output voltage ranges and similarly for input voltage ranges. So noise margin, noise is present in all real systems. This adds a random fluctuation to the voltage representing logic levels. To crop with noise, the voltage range defines the logic. The levels are more tightly constrained at the output of gate. The input, thus a small amount of noise will not affect the circuit. The maximum noise voltage that can be tolerated by a circuit, and the belows are the equations for high noise margin and low noise margin, which we have seen in the last slide. And here the same diagram has been reflected in a different fashion for understanding you. First one is for for output, and second one is for input. And this one is an example of noise margin. Here in the first one, the low noise margin for logic 0 ranges from 0 to 0.8 volt, and high noise margin for the input voltage ranges from 2 volt to 5 volt. Similarly for output, if you observe, low level output voltage ranges from 0 volt to 0.4 volt, whereas high level output voltage ranges from 2.5 volt to 5 volt. Now next one is 8, operating temperature. The temperature range in which an IC functions properly must be known. The accepted temperature ranges are 0 degree to plus 70 degree Celsius for consumer and industrial applications, and minus 55 degrees Celsius to plus 125 degrees Celsius for military purpose. So these are the different temperature ranges to operate the IC in different conditions. Ninth one is power supply requirement. Every IC needs a certain amount of electrical power to operate. The supply voltage and the amount of power required by an IC are important characteristics required to choose the proper power supply. VCC for TTL logic and VDD for CMOS logic. Power dissipation determines by ICC and VCC. So average ICC is equal to ICC high plus ICC low divided by 2, and power dissipation average is equal to ICC average into VCC. So this is the formula to calculate the power dissipation, as we have seen in the second topic in the same lecture. Now the next is current sourcing. It is related to power requirement. So here the current sourcing actions, which defines when the output of gate 1 is high, it supplies current I IH to the input of gate 2, which act essentially as a resistance to ground. The output of gate 1 is acting as a source of current for the gate 2 input. So here this one is driving gate 1 and this one is driving gate 2, which is also called as load gate. The load gate because it is connected in the output section. Here this one is a direction which is shown is nothing but it is current flowing direction, and because of this action it is called as current sourcing. Current shrinking. Here current shrinking action is nothing but input circuitry of gate 2 is represented as a resistance tied to VCC, the positive terminal of a power supply. When gate 1 output goes low, the current will flow from the input circuit of gate 2 back through the output resistance of gate 1 to ground. Circuit output that derives the input of gate 2 must be able to shrink a current, that is IIL, coming from that input. If you observe in the diagram, here the current is flowing from the VCC of gate 2 to the gate 1. So this action is called as current shrinking. Why? There is another question. Why NAND and NOR gate are so popular? So here is the answer. Logical inversion comes from free. As a result, an inverting gate needs a smaller number of transitions compared to the non-inverting one. In CMOS and in most of the other logic families, the samples gates are inverted, and the next simplest are NAND and NOR gate. Also, we can use NAND and NOR gate for simplification of any expression, for designing of any type of structure in digital families. So that's why they are more popular and widely used. To summarize the today's lecture, we have seen first one was speed, Second, power dissipation. Third, figure of merits. Fourth, fan out, fan in. Fifth, voltage parameter. Sixth, current parameter. Seven, noise immunity. Eight, operating temperature. And nine, power supply requirements. So these were the different parameters and characteristics which, which decide the performance of digital ICs. Thank you.